Exercise number 28 describes a situation where a trough is 10 feet long and its ends have the shape of isosceles triangles that are 3 feet across at the top and have a height of 1 foot. If the trough is being filled with water at a rate of 12 cubic feet per minute, how fast is the water level rising when the water is 6 inches deep? Okay, so let's get a rough sense of what's going on here. We have some sort of a trough, a water trough here, whose ends have the shape of isosceles triangles, right? So you've got this, like, I have drawn this terribly, but hopefully you can kind of imagine what's going on here. The trough is 10 feet long. The end is an isosceles triangle that is 3 feet across at the top and has a height of 1 foot. It's being filled with water, so it is not currently full. There is some water level here that will vary, and let's call that height h. Okay. We're told that it is being filled with water at a particular rate, and we're asked how fast the water level is rising when the water is 6 inches deep. The rate given is a volume, so we know that we need to relate volume to height. So we have to work this out here. Well, this is a triangular prism, so if we know the area of the end, the base of the prism, we can multiply by the height, or in this case, the length of the prism, to get the volume. So let's first find that area. Let's see here, we have area of a triangle is 1/2 base times height. Recall that base and height are basically just perpendicular measures. If you take one vertex of the triangle and drop an altitude to the opposite side, the altitude is the height and the opposite side is the base. So we have a vertex, and drop an altitude there. Although actually it would just be going, in this case, to the level of the water. We would rather not have two variables floating around. Multivariate calculus is a later course. So if we can express one of these in terms of the other, that would be good. We are told things about the height and asked things about the height, so we would like to leave the variable h as it is, and ideally express b, the base, in terms of the height. Now looking at the triangle, we see that we have the total trough, this whole big triangle, has a height of 1 foot and a base of 3 feet. So due to how similar triangles work, we can see that whatever the height is, the base of the corresponding triangle, the distance across the water level, will be 3 times that. So the base is 3h, and we have the height of h. So the area then, simplifying this, cleaning it up a little bit, is 3/2 h squared. Now the volume of the whole trough will again be this length of 10 feet times the area. So we have, multiplying there, it looks like we have 15h squared as our volume. So now we have a nice relationship between height and volume. We need to figure out how to relate the rates, and that means we need to differentiate. Now there are a few ways we can do this. The standard one that the book talks about is implicitly differentiating on both sides. And that's the method I used on the previous video that I made, because we had an implicit relationship between our quantities. Here, though, we could think of v as being a function of h, and that means we have a couple of other options. First, I'll do this with just the implicit differentiation technique, and then I'll come back at the end to show a few other bookkeeping methods that we could use if you would prefer to use those rather than the implicit differentiation. We're talking about rates of change with respect to time, right? Cubic feet per minute. So we should differentiate both sides of this. If we're using implicit differentiation, we can write it like this. We would implicitly differentiate both sides, d by dt, keeping in mind that both v and h vary with respect to time. The volume changes, the height changes. So d by dt of v is simply, of course, dv by dt, the derivative of volume with respect to time. D by dt of 15h squared, we have this constant 15. The derivative of h squared is 2h, So that gives us 30h, but h is variable, so the chain rule tells us that we also have to multiply by dh by dt. Okay. So now that we have this relationship between these derivatives, we can start plugging in the quantities that we are told. This first sentence is describing the physical situation. The trough is 10 feet long, the shape of the ends, that was all built into this original relationship here, right? We have this is our relationship between v and h. So that first sentence is taken care of. That applies throughout the entire process of the trough being filled with water. Also is the rate of 12 cubic feet per minute. That is a rate of change of the volume with respect to time. And that tells us that dv by dt is 12. Right, so let's go ahead down here and fill that in. dv by dt equals 12. We have a 30. Let's see what else we have. We are asked how fast the water level is rising when the water is 6 inches deep. Now, we're measuring all of our distances in feet here, so 6 inches is half of a foot. That's telling us that our height is currently 1/2 of a foot. And we're asked how fast the water level is rising, so that is a rate of change of the height. The dh by dt is unknown, and it is in fact what we are looking for. So solving now for dh by dt, we have 12 divided by 30 times 1/2 is 15. And simplifying a bit, there's a common factor of 3, leaving the 5, meant to say. So we have 4/5, and what are the units for the height? That would be feet per minute, are the time units there. So 4/5 of a foot per minute would be the rate of change of height. So again, as with the previous problem, we use the general information that applies universally in the situation to set up a relationship. Once we have an equation relating the quantities we need to know, we can differentiate. And after we've taken the derivatives and cleaned things up if necessary, then we can use that relationship between this equation here. This equation here is what relates the derivatives, which are rates, right? This is the related rates that we're talking about in this section. It's the relationship between the rates. And then you can plug in the specific information for just the instant, the snapshot that you're dealing with at the moment, and get this result. Now, I mentioned that there are a couple of other bookkeeping techniques we could use. From this situation here, one thing we can do, let me kind of separate these a little bit. One thing we could do is to say, all right, so we are given the rate of change of volume, that is dv by dt, right? That's the rate at which the tank is, or the trough rather, is being filled up. We're asked how fast the height changes, dh by dt. We need a relationship between these quantities. Once we fiddle around with the geometry and algebra a bit and get this equation, we can see, oh, hey, v is written as a function of h. So we could find dv by dh if we wanted to. And if you're comfortable with the Leibniz arrangement of the chain rule, you could write the appropriate chain rule relationship, which is that dv by dt is equal to dv by dh times dh by dt. Right? So once you write that chain rule, you can say, okay, now what do we know? Well, we know dv by dt. We're given that that is actually constant throughout the problem. It's safe to plug that in. That's our 12 cubic feet per minute. So you can plug in your 12 there. dv by dh, we aren't given, but we can find it from this here, right? V is a function of h. So we have 15h squared. Its derivative is 30h. And then we have the dh by dt is what's unknown. And at this point now we can plug in our h and again solve for dh by dt. We still have used the chain rule, but we actually used the chain rule earlier, right? We used the chain rule to set up this relationship, and then we started plugging in the quantities that we know about so that you didn't have to apply the chain rule as a step here. That was taken care of separately. So that's one option. Another option that some students like is, I'm running out of space here, so let's write this further down. It was v equals 15h squared. So let's come down here. I wrote that relationship as v equals 15h squared. What some students like to do when they have something like this where one variable is clearly a function of another, and there's a variable underlying all of this, v and h are both functions of t. So some students will write this as, okay, well, v is a function of t, so we can write that as v of t. And h is a function of t, so that is h of t. So we have v of t equals 15 times the square of h of t. And now we can just say, okay, well, here's v of t. Let's find its derivative, v prime of t. So we, again, use our power rule there. So we have 30 h of t, but h is a function of t. So then our chain rule tells us that we have, I don't know, I was writing function. Our chain rule tells us that we then have to multiply by h prime of t. So you can then write this, you can't get around applying the chain rule. That's usually going to be necessary. But some students find this easier than thinking about implicit differentiation in the Leibniz notation. So you might prefer to use that instead. And you see that all of this is the same. What's v prime of t? Well, that was it 12? Done this several times. Yes, okay, so that was 12. We have 30 times what was h of t? Well, h we were told is 1/2, and h prime of t is what we're trying to solve for, and then you solve for that and find that h prime of t, the rate of change of height with respect to time, is again that 4/5. So that's kind of another bookkeeping technique you can use if you want. It's a, sometimes if your relationship that you end up with is more implicit, you still might not be able to get around the implicit differentiation easily. But even then, you can still use this idea of writing everything as functions of t and then using prime marks as appropriately if you find that easier. So you do have a few options for the bookkeeping. As with many problems, there are a variety of different things. You can take different paths to the solution, but there are just certain key points that you want to make sure you hit along the way. You'll want to find at least one relationship between quantities that are given to you, and you'll probably need to take at least one derivative along the way. You'll very likely have to apply chain rule in some form or another. But, several different things that will give you the same result at the end.